Okay, so let's go to page 7. So this is basically what your quiz is going to look like on Friday. We're just going to kind of take these problems and these concepts, and we're just going to do different variations of them over the course of these next few days, and then so all these problems here is just in preparation for Friday's test. Friday's quiz. But the hope is that after we go through a couple of days of this, you'll kind of get into the rhythm of it and kind of expect and know what's going to, how to work these problems. I like this problem. I like to start off with this. There are other FRQ topics, but I like this one because this is kind of like a hodgepodge of a lot of different topics from first and second semester. And I like the fact that it kind of hits on a lot of things. So not only is it good for FRQ review, but a lot of these topics and concepts that we're going to be doing are also good for multiple choice review. So so I like to start with this because it hits the most number of things over the course of this year that we've covered in terms of the material that we've covered. Okay, so let me read the problem here. It says let f and f prime be differentiable functions. So again, differentiable just means a smooth curve. Okay, no sharp turns, no asymptotes. Okay, nothing out of the ordinary. It's no surprises. The graph is just going to be a smooth curve all the way through. Table gives values of f and its derivative f prime at selected values of x. Okay, a lot of different things are shown here. We have g of x, which is sine of 3x minus e to the cosine 2x. We have a table of values between f and f prime. So that's what this is referring to, the smooth curve all the way through. So there's no surprises. There's no sudden points and slopes that are undefined. It's all going to be, even though we're not seeing all the values in between, we know that there's not going to be any surprises for problems of values that we don't see. H of x is defined as the definite integral from 6 to x of j of t. And this is the j of x graph. So once that x gets inserted in for t, then it becomes the same graph. So this is to highlight the fact that because j and h are not the same thing. However, h is the antiderivative of j. What that tells us is that this j of x graph is really an h prime. Okay, because you know that in order for h and j, in order for these two to be equal, I gotta take the j of x graph and move it up a level. So that means j is really sitting at a level below h, which means that j is really at the h prime level. So we can also think of this as this is the h prime graph. Okay, we'll come back to that when we need it. Okay, part A. Part A says, is there a value between 1 and 5 such that f double prime is equal to -3/4? Provide an explanation for your answer. Now you can see that there's no table of values for f double prime, but we do have f prime to work with. Okay, so I want to kind of show you that this is really a problem that is kind of pushing us towards applying a theorem, and specifically mean value theorem. So mean value theorem, this is on the back of your packet there, page 24. Mean value theorem says if a function is continuous on the closed interval and differentiable on the open interval, then there exists a number on the open interval such that f prime of c is equal to the slope between the endpoints. Okay, so let me just do a quick diagram, kind of demonstrating what mean value theorem is showing us. So mean value theorem, and from a visual perspective, is this. Let's say I had a graph that was f of x, and then you're given two endpoints. So what you do is you take the slope between those endpoints, and that's what this f of b minus f of a is telling us to do, right? You find the slope between the endpoints. Whatever that slope is, that slope could be 2, it could be 3, it could be 5. That slope that we find is guaranteed to live somewhere on the curve. There is guaranteed to be a point that has an exact slope of 2, 3, or 5, or whatever slope you find between the endpoints. Okay. So the slope between the endpoints is guaranteed because it's a smooth curve and there are no sharp turns. Now, we can also take mean value theorem and adapt it for other derivatives. So in other words, if I want to guarantee a second derivative value, I can find the slope between the first derivative values. So you see how I'm basically doing mean value theorem, but I'm just pushing all the functions down one level, but it still works, right? I can still, if I had an f prime graph, I could take the slope between the endpoints of the f prime graph, and whatever that slope is, that's a guarantee for the second derivative, which is the slope of the f prime graph, for that value to exist. Okay, so basically we're doing mean value theorem, but it's just kind of adapting it for one derivative down. Okay, so we're going to take this concept and apply it for part A. Part A says, is there a value between 1 and 5 such that f double prime is equal to -3/4? Well, if I want to guarantee a slope of -3/4, if I can get that slope to show up between the endpoints, then I can guarantee that slope to exist, or that value to exist. So this is my mean value theorem application here. Okay, so you're always going to be provided endpoints if we need to find a slope between the endpoints. So let's try that. F prime of 5 minus f prime of 1 over 5 minus 1. Okay, so if I can get this value to show up as -3/4, then I can guarantee that there must be an f double prime somewhere on the graph that's going to match exactly that -3/4. Let's see if that happens. Okay, so f prime of 5, we go to our table. F prime of 5 is -2. F prime of 1 is 1. Okay. And if we reduce those values there, we get -3/4, so that does match. The slope between the endpoints is -3/4, so we're able to get this to be guaranteed, right? So we can say by MBT, since f prime is differentiable and continuous and differentiable, but there's also a good chance for us to kind of practice writing out the full conditions of mean value theorem. So continuous using brackets and differentiable using parentheses. Okay, any questions with part A? Okay, part B. Let k be the function defined by k of x equals f of j of x. Write equation for the line tangent to the graph of k at 2. So anytime we want to find the equation of tangent line, we need to find order pair, we need to find slope, and then point slope form, right? So we need to find points. Find slope, and then finally point slope form. Okay, so that's our ultimate goal there, trying to find the point, find a slope, and then we can fit that into point slope form. So let's find point first. So to find the point, we know the point is going to be defined by whatever this definition is. We have the x value, so let's insert that x value, that 2 in for x, and find k of 2. Okay, so k of 2 equals f of j of 2. Okay. No derivatives going on here, but we know that this is a composite function, so we want to kind of take one piece at a time. We know we can't just do all this in one go. We kind of have to take it piece by piece here. So let's start with j of 2, because we can figure out what j of 2 is. We have the graph to help us find j of 2. So I'm just going to find that piece inside. So j of 2, this is my j graph. So j of 2 is just equal to -1. Okay, so I'm just making that simple substitution. And now f of -1, I can go to my table. All right, f of -1 is just equal to 4. Right? Okay, so there's my points. Order pair is 2, 4. Now we can move on to finding slope. Okay, so to find slope, I need to find the derivative. To find the derivative, you guys recognize what we do with composition functions? What rule is that? It's not product rule, but it's what? A function within the function, we use chain rule. Okay, so let's review chain rule here. Yeah, so I put the important derivative rules on the back here. So chain rule says, if I want to find the derivative of a function within a function, I take the outside derivative first. So my outside is whatever's sitting outside. In this case, this is f. So I do f prime of g of x. That indicates I'm taking the outside derivative, but inside, leaving the inside alone, multiplied by the inside function's derivative. So times g prime. Okay. So if I want to apply chain rule for this setup, my outside is f, my inside is j. Outside derivative is just be f prime times j of x. I'm not ready for j of x yet, so I'm just going to write it as is. Then I'm ready for my inside derivative, so I'm ready for j, so I'm multiplied by j prime. Okay, so now that we have our full derivative, now we can involve 2. Okay, so make sure that when you do chain rule that you're not trying to do too many things at once. Okay, don't involve the number yet. You got to build the derivative first in terms of x, and then work in the 2. Just understand that you really need to take this piece by piece. You're not going to be able to do it all in one go. So let's do what we can figure out first, right? We can do j of 2, right? That's an easy one for us to find. So again, j of 2, we look at the graph. J of 2 is -1. Now, as soon as you find one thing, go ahead and substitute it, but make sure everything else stays intact, right? We haven't figured out everything else yet, so we don't want to jump too far in. We want to just make one substitution at a time, and it's just going to find its way to clean up one piece at a time as well. So I'm just making a simple substitution. J of 2 is -1, and now this becomes a little bit more manageable, because now I'm just needed to figure out f prime of -1 and j prime of 2. So f prime of -1, I can pull that from my table. So f prime of -1 is just -3, right, from the table there. And then j prime of 2, okay, we have the j graph in front of us, okay, but we want j prime of 2. So j prime, we need to, if it's derivative for a graph, that means what? We want to find the what? Slope. That's right, slope. So derivative is just a fancy word for slope. If I can find the slope of this line, I can find the slope of any point on this segment here. So I'm going to pick 2 points on this line here. The slope is negative. I'm going to go down 2 over 1. That's the slope of -2. So I know that j prime of 2 is just going to be -2. So I know that my k prime of 2 must be equal to -3 times -2, which is 6. So let's see what we have so far. We have our ordered pair, we have our slope, and now we can put it into point slope form. Okay, any questions with B? Okay, part C. Part C says find the slope of the tangent line to the graph at x equals pi. So we're still needing to find the derivative and plugging in to find the slope, but we don't have to go as far as part B. We don't have to find the equation of the tangent line. We just have to find the slope. So to find the slope of G, I have to first involve the derivative. Okay, so if you look at G here, G of x is defined as sine of 3x minus e to the cosine 2x. We're also going to apply chain rule here because there's a function within a function for each of these terms. But you notice how this is presented differently than B. So I think this is good to kind of see different variations of chain rule. You can see chain rule from a function notation standpoint. We can also see chain rule with an application within a specific function standpoint. Okay, so we're going to apply chain rule from a specific function standpoint. Let me rewrite the function so that we just have easy access to it. Okay, so let's find the derivative. We know that there's an inside portion, so we got to involve u prime. Okay, so you guys remember what's the derivative of sine of u? Cosine of u times u prime. Yeah, so anytime you say the word u prime, you're basically involving chain rule. You're taking care of that inside portion's derivative. Okay. Okay, so don't involve pi yet. We got to build the derivative in terms of x before we can work in the specific x value. Okay, so there's my derivative, cosine of u times u prime. 3 is the derivative of 3x. Okay, what's the rule for e to the u? Yeah, e to the u times u prime. And when we get to u prime, we got to take the derivative of cosine of u. What's the derivative of cosine of u? Yeah, negative sine of u times u prime. So there's like a nested chain rule here. We got to go through chain rule multiple times here. But we'll start with the e to the u here. So we know e to the u is just e to the u times u prime. And u prime is everything in the exponent. And the exponent, I got to do a separate derivative rule because there's more than one piece going on. So I got to do cosine's derivative as negative sine. And then within that parentheses, there's another term. So I got to do that derivative as well. So cosine of u becomes negative sine of u times u prime. Okay, it's a pretty messy derivative, but I think we're going to insert pi in for x and just see if we can use trig values to get it down to a more manageable answer. Okay, understand that this 3 is outside of 3 pi. We can't multiply this and make it 9 pi, right? That 3 is really a coefficient. Okay, cosine of 3 pi is same thing as cosine of pi. Cosine of pi is -1. Okay, and then all of these 3 terms are multiplied together. Okay, so e to the cosine of 2 pi. Cosine of 2 pi is 1. E to the first power is just e. Negative sine of 2 pi. Sine of 2 pi is 0. So anything times 0 is just going to be 0. So we know that all of this is just going to go away. So we're only left with -3. And that's where we can stop because it's only asking for g prime of pi. Don't have to find tangent line equation, just the slope. Okay, any questions so far? Okay, let's look at part D. Part D says find h of 4 and h prime of 4. So we know that this is referring to h of x. So I'm just going to put h of x first, and then we can see what we can do from there. So h of x is defined as the integral from 6 to x of j of t. We know j of t is the graph to the right, upper right corner. And so the integral would just have to be involving the area under the j of t graph. Okay, so there's the definition. Let's go ahead and insert 4 so that we can build h of 4. Now, I want to read the graph, but is there something that I can do to make it maybe a little bit easier for me to read the graph? Right, so typically, I like to read the graph from left to right because if I'm reading from right to left, then everything is opposite. Anything above the x-axis is negative and below is positive. It just feels confusing to try to read the graph backwards. So normally, if it was an antiderivative problem where it's just you do power rule and you plug in upper and lower bound, it doesn't matter if the bounds are out of order because it'll work itself out. But here you want to be able to visualize and you want to be able to pull the area from a physical graph. So when that happens, I typically like the bounds to be in order. So I'm going to flip the balance and pull a negative outside because I can't change the balance without making an adjustment. Okay, so that way I can just read the graph as I normally would, and then once I get that number, I can just attach a negative at the end. Okay, so let's look at 4 to 6. 4 to 6, between the graph and the x-axis, we see it's going to be this, that region there. That's a triangle. Triangle is 1/2 base times height. So 1/2, 2 times 3 will just give me 3. Okay, so I'll just replace the integral with 3, but then there's a negative sitting out there, so I know that my h of 4 is just -3. I'm just following the definition and then pulling that area from the graph. Okay, so now we also need to find h prime of 4, but before we find h prime of 4, let's get to h prime of x. All right, we got to get the derivative function before we can insert the x value in. So h prime of x means I need to find the derivative of the right side. So not f, j. Okay, so derivative of an integral, what's going to happen here? Yeah, so cancel out. Okay, so this is basically applying second theorem here. We know that this integral is sitting at a level above j. That derivative is going to drag it down so that I'm just left with that j. Now this upper bound is going to get inserted in as well. So h prime of x is just going to be j of x. So we know h prime is defined as just j of x, and that's actually easy because that just means I just need to pull the order pair from the graph. Okay, and what's j of 4? 0. Yeah, j of 4 is just the order pair on my j graph. Okay, next page, part E. Okay, does anybody still need this page? Okay. Hi, part E says, on what interval is h increasing and concave down? Justify your answer. Now, we know that this is not the h graph. However, we know the relationship here that this j of t is sitting below h. So really, this is like my h prime graph. So this is a way for us to practice reading a derivative graph. Okay, so as a reminder, if this is a derivative graph, this is not the actual shape of the graph, right? We got to be able to label and identify pieces so that we can pull the correct increase, decrease, points of inflection, concave up, concave down. So I like to start off my label by looking what's above and below the x-axis. Anything that lands above the x-axis is going to represent a positive slope. Anything that lands below the x-axis is going to represent a negative slope. Anything that's on the x-axis is a slope of 0. So if that's the case, let's see if we can get our slope sign line going. I'm always going to have my endpoints. So where are my critical points? What do you see? Okay, basically, we want to pick off the slope zeros, right? Where do we see the slope zeros? 4 and 1.5. Yeah. Okay, so what's happening between 0 and 1.5? Yeah, above the x-axis, so it's positive. Don't look at the fact that you see the graph going up and down. The fact that it's going up and down just means that you have different variations of positive slope, but everything above is still going to represent some version of positive slope. They may be different slopes, but they're all going to be rising to some degree. Okay, between 1.5 and 4, negative slope because they're all living below the x-axis, right? All this is below the x-axis. Okay. Between 4 and 6, positive slope. Okay. We also want to gather information about concavity, so let's find our points of inflection. Okay, how do we find points of inflection if we're looking at the F or H prime graph? Peaks and valleys, right? So the relative max and relative min is going to be where points of inflection is going to live, right? So 1, 3, and 5. So go ahead and put those down on your sign line. Okay, so between 0 and 1, concave up. So now we look at the slope. Okay, we look at the slope. If the H prime graph is rising, that's going to translate to be a concave up graph. Concave up. Between 1 and 3, concave down. Between 3 and 5. Between 5 and 6. Okay, so I lined them up to the best that I can here. Where do you see what graph increasing and concave down? Between what? 5. Yeah, between 5 and 6. Yeah, that's 1. Right. Between 5 and 6, I see the graph is both concave up, sorry, concave down and increasing. Anywhere else? Yeah, between 1 and 1.5. There we go. All right, increasing, concave down. Okay. Okay, part F. Find the absolute minimum, absolute max value. So anytime you see this, this is applying extreme value theorem. So extreme value theorem says test endpoints and test relative max and relative mins. So That's going to come from your H prime sign line. Right, we have our endpoints, we have our relative max, relative min. So those are the points we're going to test. We're going to test 0, 1.5, 4, and 6 into the H graph and see which H value will produce the highest and the lowest on the graph. Okay, so we start off with H of 0. Here's my H of X graph. I'm just going to replace 0 in for X. Okay, again, I like to read the graph from left to right, so I'm going to flip the bounds and change the sign. So I need to accumulate all those regions from 0 to 6. They're just various triangles of different shapes. I'll do 1/2 base times height for all of them. I already know this is 3, right? So just to speed things up here, that area triangle is 0.75. This one is negative 3.75 because it's below the x-axis, and this is positive 3. So from 0 to 6, I'm just going to add up all those values. But then I'm going to just keep track of that negative out in front there. However, it just ends up being 0, so it looks like that sign change is not going to matter. But normally, if it was a different number, we would have to make sure that we adjust for that sign change. Okay, next up, H of 1.5. Okay, we flip the bounds and change the sign. Okay, so from 1.5 to 6, that is referring to the second and third triangle, right? So we can say negative 3.75 plus 3. The negative 0.75 will cancel out with this negative in front, so positive 0.75 is the result. Okay. This is also out of order. I'm also going to change the sign and flip the bounds. 4 to 6 is just the last triangle, which we know is 3, with a negative in front, so negative 3. And then H of 6. Okay. H of 6 is just from 6 to 6. If the bounds are the same, then the area is always going to be what? 0, yeah. Okay, we have our 4 candidates. We're looking for the absolute max, absolute min. Absolute max will be 0.75, absolute min will be negative 3. Okay, part G here. Evaluate the definite integral from 1 to 3 of f double prime of 2x dx. This is kind of a way that sometimes College Board uses function notation to get you to involve U substitution. So we know we don't have 2x available, so we need to get that 2x resolved. So we'll let the parentheses be the U value. And we go through U substitution, get everything in terms of U. And then we just start making our substitutions here. By going through U substitution, we know there's a leftover 1/2. That's going to be part of my process there. Now, this is not relying on power rule, but we do know this is in general. What's going to happen if I take the antiderivative of something that's at the second derivative level? It's going to rise up to what? F prime, yep. So that's what's going to happen. I have integral of f double prime will turn into f prime. Okay, there's my antiderivative. There's my leftover coefficient. But I want to evaluate the bounds with matching variables. So I'm going to bring the x back into my answer, into my antiderivative. And now that I have my antiderivative with U substitution adjusting for that that additional coefficient, now I can work in the bounds. The variables match. My 1 and 3 are in terms of x. My antiderivative is in terms of x. So insert starting with the upper bound. 2 times 3 is 6. Minus 2 times 1 is 2. Okay, these are all values that we can find at the top of the page from our f prime graph. Sorry, f prime table. F prime of 6 is 2. F prime of 2 is 3. 2 halves minus 3 halves is negative 1/2. Okay, so we got through pages 7 and 8. Your homework is pages 9 and 10. Tomorrow I'll check pages 7 through 10 and I'll send out a reminder this afternoon.